Here we are again.
Hi everybody, it's Tony and Ian from Tektronix.
Nice to see you guys are back. We're going to do a video on FFT.
That's right, the fast Fourier transform.
Okay. So just what is it, Ian?
It's just a different way of looking at your signal. On oscilloscopes, we're used to looking at voltage changing over time. FFT just shows you instead what voltages are present at each frequency.
I get that. That's a good. Okay. So this is the kind of a clear way of looking at this.
Right, if you can imagine your signal as a bunch of wire tangled together, the FFT just helps you untangle it and see what it's made of. See what components are lurking in that signal.
Like tangled hair.
Exactly. Hey, what are you saying?
No, you're okay.
Okay. I used conditioner this morning, come on. So let's say you're designing a circuit. You're going to send some RF energy out an antenna. So you're going to pull out that antenna, plug in a B and C cable, connect it to your scope. Now because you're generating a sine wave, you expect to see the voltage changing sinusoidally over time, and that would be represented in the FFT by one spike, because there's one frequency. Exactly. You got it already.
Excellent.
But imagine that you plug this in and what you actually see is a second spike right here.
That is excellent.
And you wouldn't see that right there in the sine wave because it's so low level. It's such a minuscule second signal that you have to have something like the FFT to bring it out.
There's no way I could have seen that.
And on a real scope, you'd look and you'd find out, well, if I'm expecting 900 megahertz and I got 1800 megahertz, that's a harmonic. I probably have some harmonic distortion. There are other causes.
And this isn't just Photoshop. This is
a real,
right?
The arrow's photoshopped.
I can't believe that. It's so good.
So there are some other common causes of interference. We're just going to kind of let those sit on the slide for a second so that after the end of the video you can jump back here.
And you thought it was harmonic because where it was at.
Exactly.
In the frequency,
if it were
right?
somewhere else, maybe it would have been crosstalk from a clock signal.
That's really handy.
So let's talk about how it actually works. There's this beautiful property of mathematics where every signal can be thought of as the sum of a bunch of sine waves.
Did you hear him? He said every signal?
Any signal you want, any shape. Name a shape.
Let's do a square wave.
Square wave. By coincidence, that's what's on this next card. Yes, Tony, even a square wave is the sum of a bunch of sine waves. Let's see how that works. If we wanted to make a square wave by adding together a bunch of sine waves, we'd start with a single sine wave.
Ooh, that was smooth.
Yeah, very smooth. It's almost like we've done a bunch of failed takes of this video.
No way. This is the first
So
one.
if we add a sine wave to nothing, we get a sine wave.
Okay, 1 to 1. I got it.
Right. And that would cause a single spike to appear in the frequency domain. Now we're going to add a second sine wave that's 1/3 as tall, and it's been scaled in by 1/3.
And this is the mathematical part. This is like, there's 2 humps within this big one, all the way
Yes,
across.
exactly. When we add those two together, that's going to add a little...
Yeah.
As you say, that's going to add a little hump at the top and bottom of each of these. And in the frequency domain view, because it's 2 sine waves, that's 2 peaks. So let's add a third one. Instead of this one being scaled by 1/3, it's scaled by 1/5.
I see
And
that.
when we add that, it's going to add even more wiggles. It's going to make the sides steeper. It's going to make the tops and bottoms flatter. And you notice we're kind of closing in on a square wave here. So then we go to a 7th.
Did we say we're getting squared up here?
Oh, terrible.
Okay.
We go to a 7th and 1/9 and 1/11 and so on. And so we keep adding peaks until it kind of vanishes down into the noise floor.
Oh, yeah. And we recognize that. That goes down like that.
Now let's hang on to this
That's good.
card. We'll compare it with the real scope in a minute.
Okay.
So real world signals have this same property. They might look like a tangle in the time domain and then a nice neat shape.
And this is probably something you're familiar with. Lots of tangled signals.
Yes.
How to break them down.
So let's see this on our real scope.
Yeah. Let's take that away.
So we're going to see what this looks like on a traditional oscilloscope first. Most modern oscilloscopes have an FFT feature. They're usually in the math system. So we're going to press math, FFT, and right away you can see that signal tapering way off down in the noise floor. But let's zoom in on that a little bit.
Just like in our drawing, right? How it tapers off.
Yes. So you can see that tapering off there. In fact, I'll move it down a little bit.
Sure you know your way around on this oscilloscope, don't you?
This one feature I do. So can we get the card that we drew earlier? There we go. You can see that looks pretty much like the FFT there.
I see the angle and I see the angle.
All right.
Genius.
There's another class of instruments that also do a lot of FFTs, and that's spectrum analyzers. And this oscilloscope, the mixed domain oscilloscope, has a little bit of spectrum analyzer personality built in, and it can do FFTs as well.
Mixed domain.
Mixed domain.
Two things going together.
So we've
Seems
got
really handy. Sorry, Ian. Go
well,
ahead.
we hope it is. So we've got one signal going to both the traditional scope channel and this dedicated spectrum analyzer channel. I'm going to turn that on,
Oh,
and right away you see a difference.
I do, yeah. Both types of views are right there.
Exactly. We've got the frequency domain view in a separate view, and you can see that second peak stands right out, and we've even marked it and identified that it's spaced from the original 900 megahertz by 900 megahertz, and it's down about 25 dB.
So you put the marker in here, or did it mark it for you?
It marked it for us. So that
How
tells us
convenient.
it's probably harmonic distortion.
So this concludes our video on FFT.
Yes.
But there's
and
more, right?
There's more. If you want to learn more about FFTs, you can go to tektronix.com/FFT-basics.
And there's a lot of stuff there.
Yes.
Yeah.
And also stay tuned for the next video in this series where we do an FFT of a musical signal in front of a live audience.
Well, that sounds great.
All right. See you around.
Okay.
Thanks.